And up next, we have Amir Langer. Hello, Amir. Good afternoon.
Hello, how are you?
I'm fine. I'm fine. Great to have you here. Amir is from eBay, and he's going to talk to us about the dark side of flame graphs. Now, if you don't know this, it's definitely a project you and the tool you definitely want to explore. And Amir will give us his take on that. Amir, I'm sharing the slides, and the floor is yours.
Thank you. Okay, so my name is Amir, and I have 5 minutes to talk to you about flame graphs. And this is a flame graph. It's a visualization of a profiler results. It's sampling profiling, and at eBay we use and generate those flame graphs in production to great effect. The towers or the flames that you see in this picture are stack traces, and they are sorted alphabetically. So if 2 stack traces start with the same trace, they will be seen as one. We will have the same frame. And so we have real good navigability to see how did we arrive at a particular function and where did we go from that function. The width of every frame is the number of samples that the profiler detected for that frame. So if it's a CPU flame graphs, what we see corresponds directly to the total time the CPU spent on this stack trace. In the same picture, we can also see the self-time. The self-time is simply the edge of every frame. So if the CPU spent a lot of time executing a particular function, it will have a very large edge. If it has no edge at all, it means that frame or that function only did delegation. Flame graphs have color schemes. This is the Java color scheme, for example, and that allows you to pinpoint and know exactly what is the type of every frame in the stack trace. You can search a flame graph. You can zoom into a particular frame in the flame graph. And essentially what you have is an SVG file, and you can take that SVG file and you can show it on any browser and use it to detect a lot of performance issues. But we're here to talk about the dark side of flame graphs. There are things that we cannot see in flame graphs. Flame graphs only offer us a snapshot of the running process. So if the profiler worked for 30 seconds, this is what we see. There is no time dimension in flame graphs. There is no before or after in flame graphs. There's no ability to see 2 sets of results to compare between them. We cannot also manipulate the raw data because what we have is the SVG file. The raw data is not there anymore. When we try to do regression analysis, the most important thing for us is the comparison between 2 snapshots. So either 2 points in time or 2 different instances of the same service. And with simple flame graphs, there is no way to do this regression analysis. We created an open source project called fgrav, and in this project, we create flame graphs dynamically on the browser directly from the raw data. And that allows us to create lots of flame graph related visualizations and help us doing all sorts of performance analysis. Differential flame graphs are the way to do regression analysis, and that was already developed at Netflix, where they started with flame graphs. At Netflix, all they had was really a different color scheme. So you would draw the second flame graph, and you would color the frames either red or blue based on the growth or reduction compared to the first flame graph. We expanded this a bit, and we create a flame graph from both sets of results, and we color in only part of the frame corresponding to how much did this function, the number of samples grew or were reduced. The reason we do that is we avoid the blind spot of having a whole stack trace that completely disappeared in the second flame graph, and therefore cannot be seen. So we can see everything. We can also switch very quickly to the original color scheme because we're dynamic. And the most interesting thing is that we have the ability to manipulate the raw data. A lot of the things that we see in regression analysis is that a simple diff between two snapshots is not that trivial. In languages like Java, where whenever you call a lambda, you're actually invoking a dynamic method that is created on the fly. In your stack traces, there's an arbitrary number. And you need to filter out this arbitrary number, otherwise you reach the image that you see before you. Once you filter this out, you can see the real image, and you can see exactly what stack traces grew and what stack traces reducted. Thank you, and I'll be happy to answer any questions later in Discord. Thanks.
Thank you very much, Amir, and very powerful visualizations. Amazing how much you can condense so much data into something that can jump out of the screen and show you immediately where to focus at. Thank you
Absolutely.
very much. Great open source contribution to the community.
Thank you.
Thank you very much.